Now we have taken oxalic acid in this conical flask. For titration, we have to add phenolphthalein indicator 2 drops. Now this phenolphthalein indicator, as we know, is colorless in acidic solution, and when base is added and in basic solution, basically this turns pink. So, how to estimate the neutralization point? When this solution, this colorless solution will turn pinkish, then we can know that the neutralization point has been achieved and our titration is complete. Now, let us proceed for titration of oxalic acid with NaOH. So, now let us start the titration experiment. Now, we have taken the NaOH solution in burette and oxalic acid along with phenolphthalein indicator in the conical flask. Now, we will be adding the solution from burette dropwise. Now, how to operate this burette? You have to hold this burette by left hand, turn this knob like this slowly, and we can see dropwise NaOH comes here and a faint pink color appears, and upon stirring this color goes. So, the experiment will go on like this. We have to add NaOH dropwise from left hand, we have to operate the knob, and from the right hand we have to continuously stir this conical flask. Now, we are adding NaOH gradually dropwise. Here we can see we are almost close to the end point, since the intensity of the pink color is gradually increasing, and here with one single drop we can see we have reached this end point. This end point is marked by this pink color. The pink color shows that the entire oxalic acid has been neutralized with NaOH, and from here we have to record the volume of NaOH required. So, our titration is complete. Now, for estimating the strength of sodium hydroxide, we need to find the volume of sodium hydroxide consumed in neutralizing oxalic acid solution. Now, the sodium hydroxide was initially in 0 mark, and the final volume comes to around 2.8. So, here we have to also consider the lower meniscus of the solution, which touches the graduated mark here, that is the 2.8. So, the volume of NaOH required is 2.8. From normal calculation, we know that V1S1 equal to V2S2. Now, here the volume of oxalic acid taken was 10 ml. The concentration of oxalic acid was known, and the volume of NaOH was also can be observed from this experiment, and finally, we can estimate the concentration of NaOH. Now, we will begin the second titration, that is standardization of HCl using the previously standard NaOH solution. This HCl prepared has a rough strength of around 0.5 normal. Now, the titration process is pretty similar to the previous one. We will pipette out around 10 ml of HCl. We have to gradually adjust so that the lower meniscus of the solution touches the 0 mark, the same concept we used in case of burette. Now, we will be transferring this into the conical. After that, tap twice. Again, we will be adding 2 drops of phenolphthalein indicator. and being an acid, that is HCl, this again colorless, and again we will be titrating this with sodium hydroxide. Now, let us begin the second titration part. We have filled this burette entirely again with sodium hydroxide till 0 mark, and let us add this slowly. We will open this knob using left hand and hold the conical in the right hand, add dropwise and again stir this one. We can see a gradual appearance of pink color. What happens actually is that when NaOH is added, when one single drop falls out here, the local concentration of NaOH is very high, which shows this pink color. However, again on mixing, this is neutralized and the pink color disappears. Now, when the pink color persists, we can be sure that there is no H plus ion left which may neutralize the NaOH solution, and as a result the solution is completely neutralized, or rather excess of OH minus is there, and we have to stop this titration when the solution is pink. Now, you have to gradually add this dropwise and stir it. And one small thing out here is that if any time you feel that one of the drop has been out there in the side of the conical, inside the conical, you can use double distilled water anytime. Okay. You can just clean the sides. Please note that if you can easily use water during titration, because upon using water only the volume changes, the concentration may change, but the number of moles of the component remains same. So, titration is all about equivalence, reaching the equivalence point, that is number of moles or equivalent present in the solution. So, adding water does not change anything in the titration process. We can see the pink color is there. It may be coming within 1 to 2 drops. And here. Here finally pink color appears, that is the solution is completely neutralized, or rather a small amount of alkali is excess in the solution. Now, we have to determine the strength of HCl solution again. So, we are done with the titration process. The solution has been turned into pink. Let us see the concentration of HCl required. For this, we have to note the volume of NaOH that is utilized in this process. Here we can see this is the 0 mark, and this is the graduated mark out here where the lower meniscus touches is 8.9. So, the volume of NaOH required for titrating this HCl is 8.9 ml. Now, let us calculate the strength of HCl using V1S1 V2S2 method like the previous way. So, we have calculated and seen that the concentration of HCl that has been titrated is 0.635. Again, the concentration which you have prepared 0.5 is not exact. Being a secondary standard, the concentration of HCl that has been determined using titration method is 0.635 normal. This HCl will be used for protonation of the amino acid used for titration. Now, let us proceed for the estimation of pI of amino acids. Now, for calibration, first we will calibrate it using pH 7 standard buffer. Now, this pH 7 standard buffer has been transferred into this beaker, and the pH electrode is immersed into this beaker. Now, here we can see that the pH is not exactly 7, rather the pH is a bit lower than 7. Now, we have to calibrate it in order to reach 7. We will gradually calibrate this solution, it is increasing. Okay, now we can see it is showing pH 7, that is the pH electrode has been calibrated with this solution to pH 7. Similarly, we will calibrate it using pH 4 buffer. This one is another buffer, pH 4 standard buffer. We will calibrate it using this one, and after that we will also calibrate it using pH 9 buffer, that is pH, this is actually pH 9.2. Now, we will calibrate it using pH 4 and pH 9.2 respectively. Now, let us begin with the PI estimation. For this, we have taken this glycine solution, this is 0.1 molar glycine, and we will take around 10 ml of glycine in this beaker. Now, let us pipette out 10 ml glycine. Now, the solution lower meniscus just touch the 0 mark. I pipette out 10 ml of glycine. We are carefully taking this in this beaker, this 100 ml beaker. Again tap twice. Now, this will be used for PI estimation. We have taken this glycine solution in the beaker, this 10 ml glycine solution. Now, before beginning this with this experiment, we have to completely protonate this glycine. For this, we have to add HCl solution, the standardized HCl solution. Now, what amount of HCl should we add? The HCl should be sufficient enough to completely protonate the glycine. For this, we have to calculate the number of moles of glycine present here. That is, we have taken 0.1 molar 10 ml glycine. Now, we can calculate from V1S1 the amount of the moles of glycine present out here. Now, we have taken 10 ml of 0.1 molar glycine solution. From this, we can calculate the number of moles of glycine present here. We know the concentration of HCl, that is standardized in our just previous experiment. From this standard HCl, we have to add the fixed amount of HCl, the fixed volume of HCl, which will make up the total number of moles of HCl equal to the number of moles of glycine present. That will protonate the number of NH2, that is the equal moles of NH2 present in glycine. So, let us start the protonation process and let us add this HCl. So, before beginning with the pH titration method, so what we have to do, we have to just add distilled water to. So, before beginning, we have to add distilled water to this glycine solution. So, as we know, adding water does not basically change the number of moles, and it is required since we need to dip this pH electrode completely into the solution. So, we are adding the amount of water that is sufficient enough to immerse the electrode completely into the solution. Now, let us proceed for adding the HCl solution. Now, for calculating the amount of HCl that is required to be added here, now we have to find the number of moles of the amino acid. Number of moles of amino acid is equal to 10 into 0.1, and 10 ml of amino acid is required into 0.1 molar, and here we can see the volume of HCl required is equal to, in the simple V1S1 V2S2 method, is around 1.57 ml. So, it is not the exact one. So, around 1.57 to 1.5 ml of HCl can be added gradually, and we can see a lowering in the pH value, and we will start the experiment once we have added this HCl. So, let us add this HCl solution. We have taken this HCl, the amount of HCl to be added, we have seen it is around 1.5 ml. So, we have taken this glycine solution and in a beaker and put it in a magnetic stirrer. We have put a magnetic bar to it. We have to make sure that the bar is completely clean and free of any sort of impurities covered over it. So, let us start with this. So, before that we have to add HCl solution. pipette out HCl. We require around 1.5. I am completely making this level up to 0, so that I can just pipette out 1.5 out here. Now, we will be slowly adding this one HCl. And once you start the magnetic stirrer, here we can see there is a gradual decrease in the pH value. Now, we will slowly go on adding the required amount of HCl. We will be slowly adding this HCl out here, and we can see the pH decreases. Here we have added up to 1 ml. .4 and now 1.5. However, we can see that the pH is around 2.64. In order to check whether complete protonation has taken place or not, we may add a small amount of H plus if required, just a single drop. Here we can see there is no major changes in the pH, it is around 2.6 to 2.5. So, from here we can say that it is completely almost protonated, and we can carry out with our experiment. Now, let us start with this pH metric titration method. To determine the PI, we have to plot pH versus volume of NaOH solution. Now, for taking this reading, we have to note the volume and the amount of volume that of NaOH that is added. There will be a change in pH, we have to record the change in pH. Now, we will be recording simultaneously change in volume and change in pH. However, for recording change in volume, it is quite difficult, because one time we have to see the pH and the next time we have to jump into the burette and see the volume. In order to minimize such so this might lead to some error. In order to minimize that error, what we need to do, we need to count the number of drops. In order to estimate the volume in relation to the drops, we have to note down the number of drops corresponding to 1 ml. Now, the number of drops, what we have done earlier is that the number of drops corresponding to 1 ml is equal to 20 drops, that is 20 drops of NaOH is equal to 1 ml. Now, if we count the number of drops, write it down, suppose for 1 drop the change in pH about some x unit, we write down the pH value and the number of drops, and later on we convert that number of drops into volume. So, let us start this experiment. So, before beginning, in the beginning we have to note down this pH, that is 1.80, pH 1.80, and number of drops added here is 0. So, we write down a number of drops 0 and pH 1.80. Now, we add carefully a single drop of NaOH out here, and I can close it. And gradually increase this magnetic stirrer. We can see at around one drop, when you have added 1 drop, there is no special change in pH value, and it remains around 1.8 to 1.81. So, it is around 1.81. Now, let us add 2 drops, 1 drop, 2 drop. So, the total number of drops out here is 3, because we have added 2 drops now, and we can see that there is no significant change in the pH. So, let us add another 2 drops. we can see the pH gradually increases slightly. Now, let us add another 2 drops. And now 3 drops. Total number of drops comes out to 10, 1.84. So, we can see here that the increase in pH is very slow. So, what we can do, we can carry out with around 2 to 3 drops at a time. Okay, it is around 1.85. Let us add again 2 drops. .86, again 2 drops. Here we can see when we are adding NaOH, the pH change is very small, that is, the change in pH is not that much. The low change in pH is due to the fact that this region is basically the buffer zone. As we have studied in the theoretical part, as we have seen in the theory classes, that this is a buffer zone where the change in pH is very less, because as we know the buffer resists the change in pH. Due to buffer zone, here the change in pH is very small. Now, once this inflection point is reached, here we can see there will be a sudden jump in the pH value. So, let us go on adding. Now, gradually we can see that the pH has achieved around 3.2 to 3.3. So, here we have to be very careful about the addition of NaOH, since the inflection 4.2, 4.19. So, it has jumped again around 4.19. Again we add 1 drop. Now, here we can see the inflection point around it. It has jumped to around 6.3 to 6.2. So, it will get stabilized gradually. So, it is around 6.02. Okay. Now, it has sharply jumped to 8.2 to 8.29. So, here we have just crossed the inflection point. So, here we can see a sharp jump from pH 6 to pH 8. So, the first inflection point, so we have just crossed the first inflection point where there is a sharp change in the pH. So, this indicates that in the first inflection point there is a sharp change in the pH value, which indicates that the COOH, that is, which was completely protonated, converted into COO minus in glycine, and which gives another form where only NH3 plus is protonated and COO minus. I mean, the carboxylic, this gives another form of glycine where the NH2 plus is protonated to give NH3 plus, and this carboxylate is deprotonated and COO minus, that is, the carboxylic acid has come to carboxylate group, and again it has reached to a second buffer region where we will see again a gradual or slow rise in the pH value. So, when gradually we are adding NaOH after the first inflection point, when the value of the pH reaches around 9 to 10, the second inflection point occurs. However, what happens is that this inflection point, the change in pH out here is not that sharp like the previous one. So, we can't basically distinguish out here just by we can't actually distinguish out here just by observing the pH value where the inflection point occurs. For that, we need to plot the graph. Now, one thing it is recommended that kindly add the burette from the kindly add NaOH drop wise 1 to 2 drops as recommended. It is recommended to add NaOH 1 to 2 drops each and every time. It may take quite a long time for this titration to occur. However, if you add suppose 4 to 5 drops at a time, what may happen is that the inflection point, you might cross the inflection point, okay. And upon crossing the inflection point, the graph which you will be plotting out there will not be accurate, and the proper PI value can't be determined from that graph. It is better to add NaOH drop wise 1 to 2 drops at a time in order to get a proper inflection point from this titration. We will go on adding NaOH till the pH around 12 is reached. Once the pH around 12 has been achieved out here in the pH meter, we will stop this pH meter titration. Now, we have almost reached pH 12, we will be slowly adding 1-2 drops. However, in this region, as we can see, the change in pH is very slow, since this is completely a buffer region. Again, let us add 2 drops. So, here we can see that the pH is just above 12 or almost 12. Here we will stop this titration part, and we will go now. We will shift to the calculation part, where we will plot pH versus number of drops, which will be converted into the volume of NaOH, and from there we can calculate the PI. Now, we are done with this glycine titration. We will next move into titration of lysine with NaOH.